Greetings, everybody. So, on this video, we're going to discuss about simulating linear systems in Matlab. Okay, so let's start with the basics. We are talking about linear systems of differential equations. Okay, so this means that the differential equations are all of first order, and we don't have any nonlinear terms like squared of the states, multiplication between the states, cosine or sine of a specific state, whatever. And in order to simulate a collection of differential equations in Matlab, they all have to be first order differential equations. Okay, but I'm going to show you that this is very easily performed. Now, to simulate a linear system of differential equations, there are two ways. The first one is the more general way, which holds for both linear and nonlinear systems. And this way has to do with writing an ODE function and using a function called ODE45 or some other numbers available in order to simulate it. Now, I already have a video for ODE45, and I'm gonna put this video in the description, so you can easily find that information. But here I'm going to talk about a much simpler technique, which is called, using a state space modeling. Now, people who are familiar with automatic control systems already know what state space systems are. But let's explain. I'm going to use a very simple example here. I have this mass spring and damper system. So I have a mass M here. Q means the displacement of the mass. U is the force applied to the mass. And we have a spring with coefficient K and a damper with coefficient C. So let's say I want to simulate this system in Matlab. This system is described by this second order, differential equation. Okay, so this differential equation includes Q dot and Q double dot. Okay, so we have displacement, the derivative of displacement, velocity, and the derivative of velocity, which is acceleration. Okay, great. Now, in order to simulate this system in Matlab, I need to write two differential equations of first order describing this. This procedure is very, very easy. It's super classic in automatic controls and in what is called modern control theory. So the process is this. Depending on your situation, on your example, this may already be available to you. But let's say that this isn't available, like here. So I define one state, which is the displacement of the system, Q, and I define a second state, which is the velocity of the system. So Q dot becomes x2. So now I have two states, x1 and x2. And I'm going to replace these terms by Q becomes x1, Q dot becomes x2, and Q double dot becomes the derivative of the second state. And by this process, I'm saying this to you very fast because it is widely available for control systems theory. We can easily derive from the original differential equation two differential equations of first order, these two. Okay, and from these two differential equations, I can simply, take this set right here and simply rewrite it in matrix form, where you see U is the input. Remember, x1 is the displacement, x2 is the velocity, and the A matrix here represents the internal connection between the variables, x1 and x2. The B matrix represents the input matrix, which tells us in what states does the input go into. And by Y, we denote the output matrix. Now, generally in state space systems, by output, we define the collection of the states that we can actually measure. But here, since this is a simulation, we can easily assume that I can measure all of the states. So the first state is, I'm sorry, the first output is the first state, x1, and the second output is the second state, x2. So I can directly measure displacement, okay, and velocity. Now let's go and simulate this system in Matlab. To simulate this system in Matlab, I'm gonna put this right here so we can easily see that. Okay. Nice. I'm sorry. So I have Matlab right here opened and I have a file. And in order to simulate this model, I only need a command called a state space model. Okay, so SS or state space is a built-in command in MATLAB, and it can actually define this set of differential equations, the state space model, and the output as well. And to do that, we only need the matrices A, B, C, and in case we have an input directly into the output, we have also a matrix D, but here the matrix D is 0. So I come here in MATLAB, I define some parameters for the mass and spring and damper coefficients. These are just random ones for this example. So then I define the matrix A, just like you see right here, 0, 1, minus K over M, minus C over M, just like you see here. Then I define the matrix B, 0, and then it's 1 over M. Then I define the matrix C. Since I want to measure all the states, the matrix C is the identity matrix, right? And D is 0. This is the matrix that is possibly in some situations applied, denotes the input directly into the output, but here it is 0. Okay, so this is it. Okay, let's close this thing and go directly into MATLAB. So by defining all that and calling the system with the ss command, and I save it in a variable called sys, MATLAB immediately defines a state space model, the one that you see right here, right? So this is the state space description, A, B, C, and D matrices, which are the internal variables of the model. So now I can simulate this system. Well, if I want some specific initial conditions, I can simulate it. If I want zero initial conditions, but some specific output, input, I can also simulate it. Now, MATLAB has some built-in commands for specific types of inputs. So it has some basic inputs because they are very common in control systems. So let's say I want to simulate this spring mass system under an impulse input. Let me remind everybody, an impulse input is an input let me read this for an impulse input is an input that is applied to the system at time 0, and it basically denotes very high input force over a very, very short interval. It's pretty much like going and kicking the system at time 0. So the MATLAB has a built-in command called impulse. So I can simply write impulse, and let's see. I immediately obtain the output of the system. Okay, so this is the impulse response as you see right here. The first graph depicts the displacement, which is the first state, and the second graph depicts the velocity, which is the second state. So easily as that, I can obtain the solution for my system, right? So it is super easy and super fast. Another built-in command by MATLAB is the step response. Step response step input denotes a standard fixed energy over the whole time interval. So it's like a switch into the system. Okay, so it denotes stable input into the system. So if I write step response right here, I can immediately obtain the step response of the system. So you see the system starts from zero initial conditions. This is an understanding when you ask for a step response, it assumes that the system starts from zero. So we have a zero position and a zero velocity. And as we apply a steady force into the system oscillates, and then the derivative goes to zero, but the position of the system remains at a non-zero point, equal to 1, right? And here actually we can also see various characteristics of the system. For example, by right-clicking, I can see characteristics like the peak response. All right, you can see the peak response right here. And it also tells me at what time do I have the peak response, 3.14, and the overshoot is 72.9%. And I can see some other characteristics like the steady state, for example, which is 1. So it tells me that the steady state is 1 for the system. And I can also see a characteristic like the settling time, for example, which is 38 seconds. So you see, immediately I can obtain a lot of information about the step response of the system. Very nice. And also, apart from plotting the graph, Matlab has another option, both for the impulse and the step response. If I simply write down step into the command window, I only get the graph. But let's say I also want the variables, each individual output. So for that, Matlab has this variation of the step command, where we actually, if we run this, instead of plotting a graph, what it does, it simulates the step response and saves the time in the variable t and the output in the variable y. So if you see right here, for example, y has two columns. The first column is the first output, and the second column is the second output. I can actually, print it here. So this is the response. Okay, first column is the displacement, and the second column is the velocity, right? So I can actually save the outputs in a variable of my own. So some may ask, Lazarus, why do you want to do that? Well, let's say I want to do some statistical analysis, or I want to take this time series and then use it in another application. So there are many ways why you should probably need that. And for example, here I may want to use it to plot the phase diagrams. I don't know if you are familiar with phase diagrams. So here I have plotted the first output, I'm sorry. Here I also have the second output, but here I also have the phase diagram. Now the phase diagram is a diagram that plots the two outputs with respect to each other. So instead of plotting them with respect to time, I can also plot with respect to one another so I can see how they interchange together as time changes. So here I obtain the spiral. The system starts from here, zero initial conditions, and slowly but surely transcends, if we like, into this equilibrium position, which is zero velocity and displacement equal to 1. Okay, so just as a side note, this is called the phase diagram. This is very common in physics, for example. So impulse response, we saw step response, but there are actually other possible responses. So you can use initial. This is a command where you input the system and some initial vector, and Matlab plots the response for this specific initial condition. So we have no output and no input, I'm sorry, but this specific initial condition. So it starts from 1, 0 velocity, and you see that the system starts and oscillates back and forth until it goes back into the equilibrium position. Okay, so this is the initial condition response of the system. And also, if you want to consider any other input of your own, let's say, for example, harmonic response or something else, you can actually define a specific time that you're interested in. So here I define 25 seconds with this sampling time. I define a specific sinusoidal input, and using the command linear simulation, I can tell Matlab to plot the output under this specific input. Okay, so gray here represents the input and blue represents the specific output, right? I can use 35 seconds if you like to get a better understanding. So this is the output for 35 seconds, right? And actually this command also has a variation, and I can also tell it to consider the response under this given input and also this initial condition that I defined earlier. So I can get the complete response under non-zero initial conditions and any input that I like. The complete response or the whole response if you like. And again, I get the simulation results as I want them. Okay. lsim, by the way, comes from linear simulation, right? So this is a very simple and straightforward way to simulate linear systems in Matlab. You just have to write them in matrix form, define the matrices, and then there is a collection of built-in commands like impulse, step, and initial. And there is also the lsim command where you can define your own input, your own time, and then simulate the system for this specific input. And if you want, also for the specific set of initial conditions. Okay, so this is it. Much straightforward, very easy to do. And any questions that you have, please write them down in the comments. Thank you very much.